If you were watching this video, then that means our Canvas conference didn't work like I hoped it would this morning. So I'm hoping this video will help with today's lesson. So today's lesson was on finding the volume of a solid with known cross sections. And I think what I want to start with is at least to make sure you understand the difference between what you were doing with the volume before and what we're going to be doing now. Before, you were finding the volume of a solid form by taking a two-dimensional region and rotating it about a vertical or a horizontal line. Okay, it's not the case with these problems today. What we're going to look at is a 3D solid that if we were to slice it at any place perpendicular to the x or y axis, what we're going to see, the surface that we're going to see is going to be some known two-dimensional figure that we're very familiar with, like a square or a rectangle or a triangle. And for this particular applet, what I want to focus on is the cross sections being either a square or an equilateral triangle or a semicircle. Okay, so let's first just kind of look at this applet and kind of get a feel for what these solids look like. And this is where I'd like to start. I want you to at least note something here, that for this particular problem, these 3D solids that we're going to form have to have a region, two-dimensional region that acts as the base of the solid. For this particular problem, we're going to talk about our region being bounded by the functions y equal x squared and y equal the square root of x. So if you look over here to the right, the graph in red is the function y equal the square root of x. The graph in blue is the function y equal x squared, and we want to say that region R is the region bounded by those two. And so we're going to take that region, and what we're going to do, if we were actually trying to construct this solid, what we would think about is placing tiles with a little thickness that the cross-section of those tiles are either going to be squares, equilateral triangles, or semicircles. We're going to take tiles like that and place them in region R perpendicular to the x-axis to form a solid. Now, here's the part I want you to at least note before we really get into this, is the correspondence between a segment over here in region R. So if you look on the left, I've just picked 2 points, and if we were naming these, we'll go back when we do a problem and name these, then I'm going to be very, very much interested in the distance between those 2 points. But I want you to notice that it corresponds to a segment over here, and that segment is going to be either a side of a square, a side of an equilateral triangle, or it's going to be the diameter of the semicircle, because in a sense, when we think about placing these tiles in region R, then basically this segment over here corresponds to just one side of the tile. Okay, so again, to help you see this, I just want you to imagine that if we were to pick squares as the cross section, then again, if I were constructing it, I could just imagine placing squares as x goes from 0 to 1. Then I'm basically placing squares in region R that are perpendicular to the x-axis. And obviously, as we move across our interval 0 to 1 on the x-axis, then the size of the squares are changing. Initially, they're increasing in size, and then they start decreasing in size. Now, that's still very difficult to see what this 3D solid looks like. So let's change this a bit and give you another way of looking at it. So again, what I was just doing there is kind of this idea of thinking about placing one tile at a time as x goes from 0 to 1, and each of these tiles being a square tile that's got some thickness, and you kind of get an idea of what the solid would look like. But I think an easier way for you to see it would be this. If I keep placing more and more tiles in region R, then I'm going to form a 3D solid. And again, we're going to talk today about how we find the volume of that solid. Now, cool thing about this applet is we can actually grab hold of this 3D figure here, and we can rotate it. And we can look at it from a lot of different vantage points. The place that I really want to take a second for you to zero in on would be right here. If we turn it as such, and if we get down to n being 1. So let me change that. And I want you to imagine right here this idea. Let me get it turned a little better. Here we go. That this segment, when you draw region R over here as a two-dimensional region, and you draw this segment, vertical segment in region R, you can describe the length of it. That corresponds to this segment over here in that 3D figure on the right, except right now it doesn't look three-dimensional because I'm just showing you the XY plane, okay? But what I want you to note is that this segment over here in the two-dimensional region R that we have on the left, if I look at this in this 3D figure on the right, if I just rotate this a bit, you'll see that that segment just corresponds to a side of the square. And so I think the key idea that I want you to get out of this, we're focusing on the visualization right here, is if I can find the volume of that one piece right there, then I can use integration to add up infinitely many volumes for figures just like that across that region. And if you think about it, the thickness of this thing is going to be a change in x, and we want dx to be so small that the smaller dx gets, the more of these tiles that we can put in that region. And again, if you can describe the volume of that one piece, then we can integrate to add up the volumes of infinitely many pieces just like that on our interval 0 to 1. All right, so again, just to kind of focus in on what this one looks like, if the cross sections are squares, if they're equilateral triangles, again, just kind of focus on this one piece, this segment here. If I rotate this, corresponds to a side of the equilateral triangle, just corresponds to the side of the equilateral triangle. And if I put more triangles in there, these tiles that look as such, we can look at it even in this form, that as we move across here and we cut this thing, what we see with a cross section is a triangle regardless of where we cut it, okay? Regardless of where we cut it, the cross section is going to be a triangle. But again, another way for you to think about it is just placing in these tiles that are triangular shaped tiles, and you're placing them in there in such a way that it fills the region and forms a 3D solid. And our cross sections could also be semicircles. Again, we just kind of rotate this to get a feel for what it looks like. But again, if we just go back to the very beginning, if I change n and I change x here, as I place these semicircles in region R to form this solid, then the key thing for us to think about is this idea of if we can describe the volume of that one piece right there, just that one piece, this one piece that, again, if I were to rotate this and want to think about what this segment right here that corresponds to a like segment over here in region R, this segment that I have graphed or constructed in region R, and the segment over here in the same region R that looks like a two-dimensional region right now is nothing more than the diameter of the semicircle. And we can use that to help us find the volume of this one piece. And again, we can find the volume of that one piece, we can integrate to add up infinitely many volumes just like that and find the volume of this three-dimensional figure. So if you want to go back and look at this later to kind of get a feel for what the 3D solids look like, then please use the applet to do so. I think the key idea is just getting a feel for how you construct it, because we're not rotating anything about an axis. And the cross sections for this particular example are squares, equilateral triangles, or semicircles. And I know it's been a while since you've had geometry, but Ms. Gerard, I know, taught you well. So finding the volume of one of these pieces is not going to be difficult.